A lightning arrestor should not be used after it has been struck by lightning. The intense energy of a lightning strike can compromise the internal components of the arrestor, rendering it unable to effectively divert subsequent surges. The primary function of a lightning arrestor is to provide a low impedance path for lightning current to ground, thereby protecting downstream equipment. When lightning strikes an arrestor, it experiences a rapid and massive surge of current and voltage. This can cause several types of damage. Firstly, the internal components, such as the metal oxide varistors or MOVs, which are designed to clamp the voltage, can degrade or fail completely. These MOV are designed to sacrifice themselves to protect the connected equipment. A single lightning strike can significantly reduce their ability to clamp voltage effectively. Secondly, the surge current can create intense heat within the arrestor. This heat can melt or vaporize internal connections, causing open circuits or reduced conductivity. The structural integrity of the arrestor can also be compromised by the mechanical forces generated by the rapid expansion of materials due to the heat. Thirdly, the insulating materials within the arrestor can break down, reducing the arrestor's ability to isolate the high voltage surge from the grounded components. This breakdown can create leakage paths, allowing current to flow where it shouldn't and potentially causing a fire hazard. Therefore, after a lightning strike, the arrestor may still appear intact, but its performance will be significantly degraded. It may not be able to handle another surge, leaving the electrical system vulnerable. A lightning arrestor is a critical component in protecting electrical systems and equipment from damage caused by lightning strikes. It works by diverting the high voltage surge to ground, preventing it from reaching sensitive equipment. If a lightning arrestor has been struck by lightning, it is essential to replace it immediately. This ensures that the electrical system remains protected from future lightning strikes. Replacement is the only way to guarantee continued protection. Choosing between underground and aerial service entrance power lines involves several electrical principles. Underground service entrance offers several advantages. Firstly, there is reliability. Underground lines are inherently less susceptible to damage from storms, high winds, ice, and other environmental factors that frequently disrupt aerial cabling. This leads to a more consistent and reliable power supply, reducing the frequency of outages. Secondly, there is safety. Underground lines reduce the risk of accidental contact with energized conductors. Aerial cables can be brought down by falling trees, vehicles, or other incidents, creating a potential hazard for the public. Underground lines are insulated and buried, significantly minimizing this risk. Thirdly, there are aesthetic considerations. Underground lines eliminate the visual clutter of overhead wires and poles, improving the appearance of neighborhoods and commercial areas. This can be a significant advantage in areas where aesthetics are a priority. Fourthly, underground lines have a longer lifespan. Because they are protected from the elements and physical damage, underground cables typically last longer than aerial cables. This results in lower maintenance costs and less frequent replacements over time. Underground installations do have some disadvantages. They can be more expensive to install initially due to the cost of trenching and burying the cables. Repairs can also be more complex and time-consuming, requiring excavation to access the damaged cable. Aerial cabling is often used in rural areas or situations where underground installation is impractical or cost-prohibitive. Aerial lines are less expensive to install initially, making them an attractive option for developers or property owners with budget constraints. Repairs are generally easier and faster to perform on aerial lines, as the cables are readily accessible. However, aerial lines are more vulnerable to damage and outages. They also require regular maintenance to ensure that trees and other vegetation do not interfere with the lines. The choice between underground and aerial service entrance depends on a variety of factors, including cost, reliability requirements, environmental conditions, and aesthetic considerations. In general, underground service entrance is preferred for its reliability, safety, and aesthetic benefits, but aerial cabling may be a more practical solution in certain situations. The lifespan of a hermetic compressor in a 10-ton air handling unit, or AHU, is influenced by several factors. These include operating conditions, maintenance practices, compressor quality, and system design. Operating conditions play a significant role. Compressors operating in high temperature or high humidity environments may experience reduced lifespans due to increased stress in the components. Frequent start-stop cycles can also shorten the compressor's life, as each start-up places additional strain on the motor and mechanical parts. Proper maintenance is critical for extending the lifespan of a hermetic compressor. Regular maintenance tasks include cleaning or replacing air filters, checking refrigerant levels, and inspecting electrical connections. A dirty air filter can restrict airflow, causing the compressor to overheat and potentially fail. Low refrigerant levels can also damage the compressor by reducing its ability to cool properly. The quality of the compressor itself is another important factor. Compressors from reputable manufacturers typically have better quality components and are built to withstand more demanding operating conditions. Investing in a high-quality compressor can often result in a longer lifespan and reduced downtime. The system design also affects the compressor's lifespan. A properly designed system will ensure that the compressor operates within its specified limits and that it is adequately cooled. Oversized or undersized systems can place undue stress on the compressor, leading to premature failure. In residential and small commercial applications, a well-maintained hermetic compressor in a properly designed system can typically last for 8 to 12 years. In larger commercial and industrial applications, the lifespan can extend to 10 to 15 years. However, these are just general guidelines, and the actual lifespan can vary depending on the specific factors mentioned earlier. To maximize the lifespan of a hermetic compressor, it is essential to follow the manufacturer's recommendations for maintenance and operation. Regular inspections and timely repairs can help to identify and address potential problems before they lead to compressor failure. Firstly, keep the system clean. Regularly clean or replace air filters to ensure adequate airflow. Secondly, maintain proper refrigerant levels. Check refrigerant levels periodically and add refrigerant as needed to maintain optimal performance. Thirdly, inspect electrical connections. Check electrical connections for corrosion or loose connections and repair it as needed. Fourthly, monitor operating conditions. Monitor operating temperatures and pressures to ensure that the compressor is operating within its specified limits. Fifthly, address problems promptly. Investigate any unusual noises, vibrations, or performance issues promptly to prevent further damage. In summary, a lightning arrestor must be replaced after a strike to ensure continued protection. Underground service entrance offers reliability, safety, and aesthetic advantages over aerial cabling, though installation costs may be higher. The lifespan of a hermetic compressor depends on various factors but generally ranges from 8 to 15 years with proper maintenance and operating conditions.